that's a lot better.
That's a lot better.
Wait
Okay.
a minute. Is this still
Wait, I might.
happening? Am I on the right one?
Oh.
Oh my god.
Yikes.
I'll click again.
Hi everyone. Please sign fill in the attendance form. So we know like roughly how many people there are, so we can like get food for everyone. Also, Matthew, not entirely sure whether or not like the V-Judge has any useful problems. I put like 3 problems.
Last I remember, there's a gate very close to
Yeah,
us.
I think that's it.
So like, there's a gate in this direction. Roughly.
But it gets to 3 and 4, but
Oh, okay. Yeah. Yep. I guess
I
the
think
gate is bullshit.
I think 3 is the closest.
Bro, you can do this. What if you do unit W and then it only do unit W? Right. Yeah, click the arrow like.
I don't think
Oh,
that's
that's backward.
I don't think that's
It's downward. Keep typing. Yeah, it probably doesn't show high school. Well, I mean, worst case, you just do manual. Or maybe search in annex ray. That could work. USW annex ray. That's what I thought. Okay, so W. What if you just do high school? Maybe if oh wait, scroll up. I thought it said 5/50. That makes sense. Oh, the NSW, don't do it for. Just do 5/15. Oh, okay, that's good. Random. Yeah, that looks like it's pure. What are time now?
I think 550 high speed is like yeah, exactly.
Oh wait a minute. When did you say we should have the operator on?
Yeah, surely I change it to like 1.
Yeah. I presume it's on the slides, right?
Which is on like I assume not easily available
Oh,
here.
yeah, you have to put it on OBS. Yeah,
It's like not easily like is it easily available?
Yeah, I can just get it right now.
Okay.
Let's do it. That's a fake PNG. Thank you.
That one's like building legit.
And then see, that's a bit too big. There we go.
Like will it block content?
If you didn't put anything in the top right, okay, maybe move it to the top right.
Yep.
Yeah.
I count about 17.
Or even like bottom right. I think that should be fine.
No, that's okay. Yeah, not an issue.
Yep, I count 18, including myself.
Oh, another thing in terms of housekeeping, I think like we've sort of prepared like some things, I guess. For programming, I guess like the V judge is like something which is up. I'm not sure how many questions there are, so it's like just chuck some arbitrary problems there. In terms of maths, they have a worksheet, but it's gonna come like sometime later. Is that correct? Yeah. So yeah. That's the link, I guess, for the VJudge content. Actually, I may not have updated that link, so I'm not sure. May point to an earlier contest. Who knows? Um, and I guess like if you guys are curious, I think everyone signed the attendance form. Is that true? It's like fine. Like I guess you can like peek at the outline for today. Yeah.
Oh wait,
Yep.
wow, there's lag, streaming lag.
Yeah, yeah, yeah. There is.
Yeah, you're doing right?
Is there like a Austin? Is there a like do these work? I think if you yeah, I think if you pull this off, it will work and probably catch on the stream.
Okay. Okay, cool. Okay, let's get started. So, Gaussian elimination. So,
You need to buy
yeah.
these too.
I don't think so.
Okay, I think I
Where's
saw
the
one in
box?
the I think.
Are they?
Unless they took it.
Like where?
The keyboard drawer. Yeah.
Oh no, they're under. Okay, so we've kind of learned from 1141 and 1131 mostly. Gaussian elimination is used to do systems of linear equations. So like a quick bit of revision, we can probably do something like this, right? We have 4x plus 2y is 3, 6y plus 7z is 5, and 6x plus 9z is 1. So a system of like n linear equations with like n variables or whatever, m variables, you can express it as a matrix. So that's like fairly standard. And then we can simply do like obviously Gaussian elimination on it and then back substitute to get some of the answers. But for some interesting bits of it, I think is just what kind of problems can you change into a system of linear equation. So a pretty interesting example is this like little lights out game. So you might have like seen it before. Is the statement generally goes like this, right? You have a grid, usually a square grid of like light bulbs, I guess. And for any light bulb you like press, it will activate or slash deactivate the 4 adjacent ones next to it as well. So like let's say you press like this square, the top, bottom, left, and right will also get toggled. So the general form of the problem is just asks like how would you turn all of the lights off, right? Let's just say we have the normal question like a 5x5 grid. Given any sort of initial state of lights, can we always turn them all like always turn all of them off? And if so, how do we do it? And if not, is like, can you give an example where it's impossible to solve? And after that, like the next logical question will be like generalizing, right? Like, is this specific to a 5x5 grid? What about like any like larger grids or even like a non-square grid, I guess. So I think the first insight is to just like after you play around with it, you'll quickly notice that pressing a button twice is kind of like not pressing at all, right? It doesn't really matter what order of lights you press because it's for each individual light, you either just press it or you don't, since the order of like pressing them doesn't matter. So you can probably abstract the lights into some sort of like variable, specifically like a binary one, right? So we can let the each light, like pressing a specific light, it be equivalent to like addition modulo 2. What I mean is like we can let 0 be the state of the light being off and 1 being the state of the light being on. So pressing it twice is like 1 plus 1, which is equivalent to 0 modulo 2. And that is like that corresponds to pressing a light twice is like doing nothing, right? So that's fairly nice. And then so after that, you can just say like for like a 3x3 board, let xij be a variable that represents whether we press the cell at row I or column j. So for example, for the top left corner, to end up off, we need the initial state and the toggles affecting it to be equivalent mod 2. So basically what that's saying is like, if the light is, let's say, off at the start, right, the number of lights you press that affect the top left corner has to be an even number, right? You can think of it as like, if you press it an odd number of times, it will remain on. So if you press it even number of times, it will remain off, which is what you want. And same thing for the other version. Like if initially it's on, you have to affect it an odd number of times to turn it off. So if you just list down all the lights that affect the top left corner, which in this case will be the one directly below it and the one directly to the right of it, you can just establish an equation like this, right? x11 plus x12 plus x21 is equivalent to b11 mod 2, where b is just initial state of the top left light. So something like that is nice because we have our, well, linear equation. It's currently mod 2, but we can deal with that later. Right? So the next step is to kind of vectorize the grid, because the issue right now is we have a square grid, I guess just a grid of lights to turn on and off. And for linear algebra, we're kind of like solving for whether to turn each light on or off, right? So we like to convert that grid into some sort of vector. You can do this by like any like method you want. Like a pretty obvious one is to just do it like left to right, top to bottom. So you have a 3x3 grid, like 1, 2, 3, 4, 5, 6, 7, 8, 9. It just turns into a vertical vector of 1 to 9. So like strictly speaking, like we map each cell to a unique index using k is I minus 1 m plus j, where m is like the number of rows, number of columns. So yeah, like that. And then afterwards, you can kind of like manually write out each set of like equations, right? For each grid, each light cell in the grid, you can establish some sort of linear equation. So obviously for a corner, we have what we had earlier, right? The only lights that affect a corner light is itself and its 2 neighbors. And for an edge, it will be itself and its 3 neighbors. So you have 4 variables, and then for a center, it will be 5 variables, right? You have the light itself and the top, left, bottom, right. So this is nice because finally you have a system of equation describing every single light, and we can just turn that into some sort of matrix, right? So if we have some sort of initial state B representing using our vector as described in the earlier slide, and some sort of like adjacency matrix of A, where A is just the matrix representing all of these sets of linear equations, we're essentially solving for x again, right? This turns into like once again like ax plus b. And what can we do with ax plus b? Like many things. We can like, well, obviously Gaussian elimination or whatever, just find the inverse. So that is very nice. So basically what we're saying is for any n by n board, we can express the entire lights out puzzle as this system of n times n linear equations. Note that this is no longer an n by n grid, it's an n times n by nm by nm grid. So the main issue with doing this is that the grid is pretty big. But if you were able to do it, then you can just, it's as simple as solving this linear equation. And from here, we can like answer our previous questions about generalizing to just answers with like questions with linear algebra, right? For example, can this be generalized? Yes, right? It will just affect the dimensions of the matrix. Is it possible for all states? Well, that will obviously depend on B, right? Like if a specific state B is solvable, that means, right, AX, the image of AX contains B, right? B is like in the image of A, yeah. And then finally, it's like, the strategy is just x, right? Remember x is our vector of 1s and 0s representing whether each light should be flipped on or off. So for any grid, the solution would be just x of telling us which buttons to press. So do you want to say anything?
Sure. Your thing's done, right?
Yeah, I'm thinking.
I guess like, did anyone have any questions about that? I think it was like covered pretty quickly. hopefully like everyone's like not that confused. I think the idea, like the crucial idea, is sort of something like this. Like with every cell, you basically can build like, I think, this equation, which just states um like if x11 represents like whether or not we toggle a particular cell. So that's like if like one x sub 11 means like the cell at 1, 1, do we toggle it or not? If you add up all of these, the claim is that it must be equal to its initial value mod 2. The reason why is because like if it's initially 1, we need to hit it like 1 time or like 3 times or 5 times in general, like an odd number of times to get it to an even state, i.e. 0, which is like where we want all of our lights to be, right? So that's sort of the claim. You can think of each of these cells as representing a variable, which is either 0 or 1, meaning whether or not we turn on or off, like we touch this cell or we don't touch this cell in a solution. And then the idea is that like once you have a system of equations, notice how there are like a total of nm variables. Once you have a system of equations with nm variables, you are able to solve it using like any form of like algorithm. In this case, Gaussian elimination should be able to row reduce it enough so you can like do back substitution to recover your original variables. Does that sort of make sense to everyone? Like I think I sort of have a bit more like application stuff here, not necessarily like explicitly written out, but I think like something interesting to maybe think about. Wonder if I can like. Okay, whatever. I'll just draw with one hand. Okay, that's fine. So, huh? Yeah, but then people on stream can't see it. Not like anyone's watching the stream. Is he? Tell him to send something in the chat then. Okay, so I think another interesting application of Gaussian elimination, something which I think Matthew and I did. Matthew's like the guy here. So a while ago we were trying to build an algorithm to solve Minesweeper. So are we aware of like what Minesweeper is? So like the idea is like you have basically a board of like some cells are like mines and other cells are like not mines, and basically like you're given a like my drawing's very small, but you're given like for example a cell. Let's say if this cell shows 3, it means like among all the uncovered cells in this like 3x3 region, exactly 3 of them are mines. And so like part of the game is like you come up with some like logic to figure out like, oh, like maybe like what's a mine and what's not a mine. Okay, example. So okay, so you can see here, this cell's a 1, which means like since the only uncovered cell is like here, we know that this must be a mine, so we can flag that, right? Now, since this cell has seen 1 mine, we know that this cell must be safe because like there's exactly 1 mine in this region, so we can reveal that, and you can like keep like solving this grid, right? Like I'm not gonna solve this grid, I'm like a bit slow. Yeah, so this is called like chording. Okay, this is like not maths, but like you can like if you flag something and so let's say this let me flag something else. Okay, like let's say this 2 has seen all of seen exactly 2 flags. If I right click and left click at the same time, I perform what's called a chord, which like clears all the cells which are like still, like I can do this quickly, right? So yeah, it's like speed running strategy. Anyway, it's like not really relevant. So does everyone understand how the game Minesweeper works? Okay, fine. So we can solve a couple things with logic. I think like some very simple rules. If like a number is shown and like there is only like that many free spots or like cells which are not yet released, we know that they must all be mines. So like for example, let's say like we know that like these 3, I guess like if we see 3 here and we know that like there are 3 mines already marked, then all of these are safe, right? So we can like clear all of those. Likewise, if you see, for instance, a cell where like everything's safe, except for like 1 spot, you know that this has to be a mine, right? So you can use some logic to deduce most of it. But it comes to a point where like logic can only take you so far, and there's like some pretty interesting arrangements. And you learn these if you like are speedrunning Minesweeper, or like trying to get good at the game. But like as an example, let's say you're on the edge of a map, and all of these are like safe. Everything underneath is safe, and you see like a 1-1 pattern. Like this requires a bit of like brain. You know that like one of these two must be a mine, and since this one sees both of these, you know that this one must be free. Does that make sense? It's like a bit of an interesting logic thing. I wonder if I can like find a game where like I actually use that. Okay. Okay. Terrible. Okay. Can we re-roll? Okay. It's also a. Okay. Maybe I should go hard. Hard probably has better situation. Um. Okay. Like this is a good example. Okay. Like take a look at this bottom area, right? So this very bottom corner, we can see that this one sees these two cells, which means that one of these two cells must be a flag, right? Must be a mine. Now this one also sees these two cells, which means since one of these is a mine, this one already sees one mine, and so all of these are free. Like these three are all free. Does that make sense? And like so there are like more complicated patterns, and obviously like Matthew and I thought about it. We were not gonna like hard code all the like available patterns, and so the idea is you can actually represent this Minesweeper game as sort of a system of equations where like each cell on the border, which has not yet been revealed, is a variable, right? And this is again a 0 or 1 depending on whether or not it's a mine or not. And if you think about it, all a cell with a number says is that everything, the sum of everything, all the variables in its 8x8 must add to the number in its cell. Does that make sense? So you can think about it as if there's a 1 here, and there are some unrevealed cells, x1, x2, x3, and let's say for like argument's sake, these are all 1s and like these are 0s or something. What this means is that what this cell tells us is that x1 plus x2 plus x3 must be equal to 1. So that's an equation we can do, right? And the idea is if you form a bunch of these equations, you'll end up with like some variables which are fixed and some variables which are like not fixed, right? And so the idea is you basically perform Gaussian elimination on like this massive set of variables at every step, and then you determine which ones have to be a fixed value. So which ones are sort of free variables and which ones have to be fixed, i.e. 0 or 1. And what that means is in all possible scenarios of the problem, in all possible assignments of variables, we know that like this cell must necessarily be a mine or this cell must necessarily be free. And so we can solve like that. Does that make sense? So that's sort of like another application, sort of like a bit more like impromptu, but does everyone sort of understand that? So the whole yeah. Um like x1, x2, x3 are just like arbitrary names I gave to the variables. Like each of these variables can take on either a value of 0 or 1. And then these are just like cells which have been revealed and like aren't in consideration. So like these cells are definitely not bomb cells. Like they're definitely not mine cells. Like you can think of them as like these like brown tiles. Yeah. So each green cell has on the border has like a variable associated with it, which is just like whether or not it could contain a bomb or not. Yeah. Like x1 equals 0 means like no bomb. x1 equals 1 means bomb. Yep. So the numbers on the screen here basically give you the equation. So let's say this was a variable a, this was a variable b. We know because of this 1, a plus b equals 1. Right? So this 1 looks at all of the cells in its 3x3 and determines that what like the sum of all the bombs inside this region must equal 1. That's pretty much the idea. And so like if this was a variable a, this was a variable b, we don't know what their values are, but we know that the sum must be equal to 1. Yeah? And if you see here, the sum of this and this must also be like the sum of these three must be equal to 1 as well. Now, if you take these two equations and like stitch them together, i.e. you think of them as simultaneous equations, you'll realize that in all possible cases, this must be not a mine. So you can like perform like maths like that. That's pretty much what the algorithm does. Huh? Why does this one become 2? The number here just tells you like how many mines are there in this region. So like each number on this grid, which is like revealed, tells you like how many like mines does this cell see, right? And it's like 3 by 3. So this thing is a 2, which means the sum of all of these cells must be equal to 2. That's what it means. Does that make sense? Like sort of. Okay. Does anyone have any sort of like other questions about this? So it's just like an application of yeah. Anyway, I think like I sort of had a more interesting thing to talk about. So this is more like programming based. So I think the 4128 people will find this like relevant. So let's consider a question. This question is called repeated multiplication. So you're given a positive integer a, and you're given a positive integer n. Your job is to compute like a to the n mod some number, like programmatically. So how do we think we can do this? Like naively, like let's say like n was small. Is there like a idea that we could come up with that sort of like computes this in reasonable time? Yeah? Yeah, excellent, right? So what we'd like to do is just like multiply 1 by a like a total of n times. So like you start with 1 and you just like keep multiplying by a, and you do that like n times, right? And we reduce like mod 10 to the 9 plus 7 as we go, right? That's not really an issue. What's the time complexity of this solution? Hopefully everyone's somewhat like okay with time complexity. Time complexity is just like as a function of the inputs, approximately how many operations the program will take. So like for example, O of 1 means like roughly no matter what you give as input, it will be like roughly takes the same amount of time. Like O of n is like if you give bigger inputs, if you give like twice the input size, it'll like perform twice as slow and it'll do like twice as many operations. I guess like what's the time complexity of like this solution where we just like multiply 1 by a n times? Assuming like multiplication is O of 1. Yeah, right? Does that make sense, everyone? Yeah, okay. So this is like not great because like when n is 10 to the 9, you're doing like a billion operations per second, and that doesn't necessarily pass. Like typically when we write programs, we sort of want them to like programs can roughly run like 10 to the 8 or 10 to the 7 operations in 1 second. Like this might take like 10 or 100 seconds, which is like fine, I guess. But if you're in a competition, you sort of have to write code for it to be like fast and lie within 1 second. That's pretty bad. So how can we do any less than n multiplications? This is maybe something which people have seen before. Let's try to calculate like 3 to the 8 by hand. I don't think we're gonna like multiply by 3 8 times. I think like maybe an example of something that we'd do is like write 3 to the 8 as like 3 to the 4 times 3 to the 4. And I guess like if you know 3 to the 4 is 81, you're just done. But otherwise, you can do like 9 times 9 times 9 times 9, right? So you can split again. And then so in this case, instead of doing 8 multiplications, we're only doing like 3 multiplications. Or like technically a bit more, but. So does that make sense? So instead of multiplying like 8 times, we can split our exponent by half and multiply instead, right? So this idea is often called like divide and conquer. The idea is let's consider a recursive process which computes a to the n, right? If n is 0 or 1, we're sort of done. It's either like, oh, sorry, it's 1 or a trivially. I can't do maths. But yeah, it's either 1 or a. Otherwise, if n is even, we should compute like, we should basically halve the exponent and multiply the 2, right? They're going to be the same value. We can just multiply the 2. Otherwise, we're just going to compute like this times a. Does that make sense? So we're just going to add an extra a at the front because like it's not even, it's odd. So the time complexity of this is log n because we like recurse or we split at most like log n times. Like in practice, you'd only compute this once and then like you'd like square it or you just like multiply by itself. You wouldn't like call this function twice. So we split at most log n times, then we can compute this in log n. Does that make sense? So our exponent reduces by half every time. So the worst case scenario is like we, like log is log base 2, by the way. It just means like after log base 2 iterations would probably be at either n equals 0 or n equals 1. Make sense? So our time complexity is log n. So we've turned like O of, we can basically do exponentiation in log n. Does everyone sort of understand that? Sure. So this is the main problem that I'm going to be looking at today. It's called Fibonacci redux. So, okay, you've earned international acclaim for your ability to find the nth Fibonacci number under like increasingly tight time limits, right? So do we all remember what the Fibonacci number is? Yeah. So it's like fk is like defined recursively. You take like the two previous ones, you add them, and you get the next thing, right? You recall the days where you like relied on some like recursion, and then like you reflect on like the first time you optimized like O of n, whatever. So now you're sort of want to try a harder problem, right? Like you want to like pursue greater challenges which are like better worth your time. The question is to find the nth Fibonacci number. So maybe you guys are excited to see the bounds. We need to solve it for n less than or equal to 10 to the 18. So basically a 64-bit integer. So yeah, that's the problem. Does that problem make sense, everyone? So we want to find the nth Fibonacci number, and n can go like all the way up to like 10 to the 18. So if you sort of like know things about time complexity, you know like, okay, n is like roughly 10 to 18, we're going to look for like an O of n or O of like log n solution. Like how is this even possible, right? I guess like there is a closed form for Fibonacci, so we could consider that. Do we remember like this form of the Fibonacci sequence? So you can compute the nth Fibonacci term like this. So you can do like phi to the n minus phi conjugate to n on root 5. Phi is like the golden ratio, and phi conjugate is like 1 minus root 5 on 2 instead. So there is a closed form, right? So like maybe we can compute an O of 1, right? I guess like maybe not O of 1, because like phi to the n and phi to the requires like exponentiation. You can do like the previous trick with like fast exponentiation, right? You can compute those in log n. So which means like theoretically we can get like a log n solution, right? Like right? Like probably not. I think there are some issues. Firstly, phi is irrational. Processing non-integer I think you guys have probably all worked with doubles if you've done programming before. Not very pleasant. They have like lots of issues, especially for large n. You can get like a lot of like error accumulation. And you know like phi isn't even like a rational number. It's like square root something, so it's like pretty sad. Also some issues. Modding a float by like 1e9 plus 7. Like what are we doing, right? Like pack it up. And also like you have to take the mod inverse of an irrational number because there's a root 5 on the bottom. So for like the 4128 people, like you'll learn about modular inverses maybe in like maths. The idea, like the maths topic, but the idea is like you can't really divide if you're taking mod something. You just like multiply by the modular inverse. So that's something you have to do. Since there's a root 5, you have to mod inverse an irrational number. Doesn't really make sense, right? So we can't really use the closed form. How can we like solve it like good? It's like a good question. Okay, so let's think about this. Yeah. Is that true? As in, if you round this to the nearest integer? Yeah. Like, the actual, like, if you evaluate this, this will give an integer. It's just like not obvious how you would actually compute like the intermediate values. Like, there's a lot of intermediate values you have to deal with. Yep. Okay, sure. Okay, fine. Let's say that that's true. I'm not sure if that's true. But it's like still not obvious how you'd like compute that or compute the intermediate like non-integer values. So I guess like let's think about like how we can maybe solve this problem. What actually categorizes our position? I.e., what do we need to know in order to get from knowing fk to like f of k plus 1? Well, we probably want to know like fk and fk minus 1, right? Because they sum to the next value. So in some sense, we can recall our state, or we can like store our state as like these two values, fk and fk minus 1. So this is our state when we are at the kth Fibonacci number, right? We need to know our current Fibonacci number, but we also need to know the previous one. So this might look a little bit different from like the DP solution that you're familiar with, but bear with me. So the idea is, how do we actually get from fk minus 1 to our new state? Well, our new state is fk plus 1 fk, right? So what we're actually doing is like we want to move from fk minus 1 to fk plus fk minus 1 and then fk, right? This is our new state. So to get from the kth Fibonacci number to the k plus 1 Fibonacci number, we need to make our state from this into this. Make sense? So what this looks like is actually some sort of linear transformation, and I think like we'll cover this later, but whatever. So it actually looks pretty interesting. If you have like this state fk minus 1, and you like transition it into fk plus fk minus 1 fk, that's the same as like xy transitioning into x plus yx, right? Like we just subbed x to be f of k and y to be f of k minus 1. So can we see how like in some sense we're basically taking a vector and like turning it into another vector? Yeah? So this will be covered in more details, but we can represent this with a matrix. So basically turning this like vector into this vector is the same as multiplying xy by some special matrix. So is anyone like unclear why this is true? Is anyone like not convinced that this is true? Okay, I'll assume like everyone's happy with the fact that this is true. If you just do the matrix multiplication, you can see like x or like this component gets mapped to 1, 1, so you get like xx, and you super impose that with like y, which gets mapped to 1, 0, so it's like plus y plus 0. So this is like the correct matrix. So basically, moving from the kth Fibonacci number to the k plus 1 Fibonacci number just looks like left multiplying our like state vector by a, right? So we take our state vector and we multiply by a. That will give us like the next Fibonacci number, yeah? Or like it will give us the next state. So basically, let's think about what we're actually doing. We're going to start with the state vector, like f1, f0, which is like, we know that it's like 1, 0. Then to get the next one, we're going to like multiply by a. So we're just going to like take this vector, we're going to like transform it through this matrix. That will give us like f1 plus f0 and then f1, which will be like the next Fibonacci number. To get the third one, we're going to like do the same thing. Now what I'm actually going to do is like replace this with the transformed version of the first one, right? And this is just a squared, or the matrix times the matrix times this thing. Does that make sense? So actually, if you notice a pattern, the n Fibonacci number is just like you take this matrix to the power of n minus 1, and then you multiply it with like 1, 0. Does this make sense to everyone? Yep. So like we're just getting the x coordinate of like this, whatever happens there, right? So we take our 1, 0, we take our like I hat basis vector or whatever, we chuck it through like a to the power of n minus 1. So really, the idea is we just need to find a to the k minus 1 for some k, right? So how are we going to do this? We need to compute this in log n. Well, it's like almost the same as our like exponentiation like problem at the beginning, but now like instead of a number, we have like a matrix. But that's still okay, we can still do it. So we're going to recall our fast exponentiation technique, which is we're basically going to split a to the k into like a to the k on 2 times a to the k on 2, right? For if a is even, and then like times an a if it's odd, yeah? So we're doing this. Since a and its powers are always like 2 by 2 matrices, multiplying the matrix is like constant time. It takes like 8 operations to do that, which is like basically O of 1 anyway. Like why does it take 8 operations? It's just like you simulate it manually. So however you would do it by hand, you can do it on the computer. It's like O of 1. And then we do like log n multiplications. So our final time complexity for computing this matrix is log n. Does that make sense? So we're splitting the exponent log n times, and then each time we're going to perform a multiplication. Multiplication is constant time for small enough matrices. So we can actually find the n Fibonacci number in log n. Yay! In fact, for big values of n, the bottleneck isn't actually the finding the matrix exponentiation, it's dividing n by 2. That's actually the more difficult part, I think. So interviewers will be very impressed, I'm sure. So in general, in fact, like this is like I've talked about like Fibonacci, right? Fibonacci is like a second order recurrence. It's like you add the previous term and then the term before that. In fact, linear recurrences of order n, you can basically write the transition matrix as like a n by n matrix, and you can just like exponentiate it like some number of times, like k times. So like multiplying an n by n matrix is slow. I think like the practical algorithm for this is like n to the 2.8. So yeah, that's the time complexity of matrix multiplication. And you can call this like technique, or like we call this fast matrix exponentiation. So you can do this. This is like an interesting thing. I think this is like something which is covered in the maths topic. So you can use this to speed up like linear recurrences or computation of linear recurrences, as long as your matrices are relatively small. So does that make sense to everyone? So yes, Fibonacci and log.
Hope everyone's hyped for diagonalization. I mean, this is a pretty powerful tool, and yeah, we'll be going through some interesting scenarios after some basic introduction. So, I mean, this is prior knowledge, just saying for the rest of our slides, but here's the key takeaway of matrix diagonalization. Any matrix A can be split into a product of three matrices, where the middle matrix is the so-called diagonal matrix, and the left matrix is the matrix of eigenvectors, and the right one is the inverse of it. So there are actually some conditions set by this definition. So that is fundamentally what we're trying to do with diagonalization. Now, just some key sort of intuition as to why we want to do it is that if we can split this into this form, let's just ignore the P and the P inverse for a moment. But the main thing over here is that this is normally going to be a vector of eigenvectors multiplied by the identity matrix, such that when you do matrix exponentiation, like say put an n here, what's actually going to happen is we can sort of absorb the n into wherever our eigenvalues are, and that'll make it faster for computation, at least from a manual point of view. I'm not sure about the computational point of view through a computer, but yes. And now we have the following conditions. So firstly, A must be a square matrix. To actually diagonalize a matrix, it must have the right dimension, because A is n times n. I mean, if we assume it's n times n, PDP and PDP inverse, they all need to be n times n. Now, the rationale is for a matrix to actually have an inverse, they need to be square matrices, which is why these sort of conditions result in A having to be a square matrix. So that is a key condition. And the other one is A must have dim A independent eigenvectors. The reasoning for that is you need distinct eigenvectors to have an inverse, like, because ultimately if you have like some stuff here and then a bunch of zeros, the inverse isn't gonna happen properly, yes. And yeah, those are the two conditions. But my question is, what are eigenvalues and eigenvectors? I hope people remember that. Otherwise, if not, we will introduce what they are. So this is the main definition of eigenvalues and eigenvectors. So eigenvalues are the lambdas and eigenvectors are the v's. The lambdas belong to a certain scalar field we have defined. In this case, they will be a part of, yes, yeah, they'll be a part, they should be a part of F2, sorry, that was a typo. Yeah, they'll be a part of F2. Meanwhile, our V's will be a part of a field F1. Now, a funny thing is, I actually almost forgot about this property, but you could consider these eigenvectors as having the special property of belonging in the kernel of A minus lambda I. So if you guys remember this equation, AV equals to lambda V, and just do a neat little so-called factorization, you guys will realize something. The definition of a kernel involves the solutions to a matrix like in this form that equals to 0 when multiplied by a certain vector. These vectors are in the kernel. So which is why we can say the eigenvector should be in the kernel of a minus lambda I, where lambda are all the possible eigenvalues. Yes, so more generally, thanks to Jeff, in terms of generalizing it, we look at pardon? We look at all k vectors such that this equation is satisfied. Any initial questions about just the fundamentals before we get to the tastier part? I'll take that as a no, I guess. And yes, these two properties are going to come in very handy. I'm actually quite excited to tell you guys on how powerful these two properties will be for the next two examples we're discussing. But basically, the sum of eigenvalues equals the trace of a matrix, and the product of eigenvalues equals the determinant of a matrix. So if we have a matrix just like this, the trace is just the sum of all its left-right diagonal entries, like just the sum of these. Meanwhile, the determinant, well, you have formulas for computing it, but in, I guess, the most simplest sort of formulaic form, it is actually the alternating sum of the entries in the first row, like going through here, times the cofactor matrix determinant. Now, cofactor is just this formula applied in recursion. That would be a good explanation for another time, since our main focus is diagonalization. But yes. And here's the procedure for matrix diagonalization. So we first must find its eigenvalues and eigenvectors as discussed. Now, the process of finding eigenvalues is to solve this equation for the characteristic eigenvalue polynomial that the determinant of a minus lambda I equals to 0. However, there is a really nice trick. This trick's gonna come in so handy. It only applies to degree 2, or I mean, yes, degree 2 characteristic polynomials for lambda. But note that the trace is actually the sum of all eigenvalues. So that's sort of like the sum of roots, if people remember Vieta's formula. And the determinant is the product of roots, which is why our characteristics polynomial for a two-dimensional matrix only, like 2 by 2, can be very simply considered as lambda squared minus the trace times the lambda plus the determinant equal to 0. So this is a very fast way. They've actually used this in competitions as well as a neat little shortcut. But more generally, you would just solve that. The determinant of a minus lambda I equals to 0. Try to find all the lambdas. The reason we do this, though, is because we do not want the trivial v equal to the 0 vector as a solution. Because if you guys look at this equation again, I mean, I do hope people can see this clearly. Like, one trivial solution for the eigenvector would be v equal to 0, but we are specifically not looking for those. Now, to actually avoid that situation from happening, like, this is our equation if we actually do the factorization. So to actually prevent that situation from happening, we need to make sure that this guy is not invertible such that it would create a v equals to 0, which is why the determinant must equal to 0 instead of being non-zero, and which is why we solve that. I hope that part was straightforward. Yes? This one, or yup, it assumes there's two solutions just for this. Yup. Yes, I mean that could technically result in just one solution, but yes, I'm only talking about 2 by 2 matrices just for that formula. No problems. And now, after we have found our eigenvalues, here comes the very long and tedious part. Now, you guys will probably laugh at how primitive this sounds, but literally, all we do is, given this equation, a minus lambda I, v equals to 0, we substitute all the eigenvalues we have found and simply solve via Gaussian elimination for our v's. Now, there is one nice, I believe, theorem I would like to point out, that each distinct eigenvalue results in a distinct eigenvector, which may help with later questions. And I guess once we have found our eigenvectors, the next steps would be literally constructing the diagonalized form, which has been described above and previously. And yes, do note that all the eigenvalues do not need to be distinct, because there are cases where one eigenvalue results in multiple eigenvectors. That is possible. And here's a simple example. We can actually live solve it out, I believe, very quickly. So yeah, this is quite a simple example. Oh, thanks, Brendan. Yep. So our first task is to actually find the eigenvalues. Now, generally you would try to solve that equation, but remember our fast method for 2 by 2 matrices only, lambda squared minus trace times lambda plus the determinant equals to 0. If you notice, the trace is 1 plus 1 equaling to 2 right across that diagonal. So we can substitute 2 in right here. And now the determinant for two-dimensional matrices, it's the main AD minus BC formula, which, just to recall for people, is if you have a matrix with entries A, B, C, D in this order, the determinant is AD minus BC. And if you apply that formula here, you get 1 times 1 minus 1 times minus 1. So it's 1 minus 1, which equals to 0. So our determinant is 0. And this results in lambda minus 2 equals to 0. So our two eigenvalues are 0 and 2. I hope that part was straightforward. But you can do it that way too, by just calling the determinant equation out, which is the more general approach. And our next job is to find eigenvectors. Now this is a tedious job of substitution, but just to visualize, since you lose a degree of freedom in this process, the idea is, if we set up our system right there, so let's say for lambda equals to 2, A minus 2 times the identity matrix would be equal to 1 minus 2, that's negative 1. The other negative 1 stays, negative 1. And that 1 minus 2 is also negative 1. So you have a matrix with 4 negative 1s. And when you try row reducing it, if I denote these entries as v1, v2 of their own nature, I would get v1 equals to minus v2. And that could be construed as an arbitrary, say, scalar v1 times 1 minus 1. And that is the rationale through which you will extract the eigenvectors. And yes, 1 minus 1 was one of our entries for lambda equals 2. I hope that part was straightforward. Our next part would be basically to substitute these into our equation for diagonalizing. And after that, now this is a trick that only works for two-dimensional matrices, but you have the fact that the inverse of, say, a two-dimensional ABCD matrix is 1 over the determinant of that matrix times having the AD entries swapped around to DA and negative signs applied here. That is what we have actually used to quickly compute out for just two-dimensional matrices. Otherwise, if you were to find the inverse for matrices with greater dimensions, like 3 by 3s, you'd have to essentially do Gaussian elimination again, trying to solve this equation So you'd be solving essentially against in the other column against the identity matrix, and once you do Gaussian elimination, you'll find the inverse matrix. Yes. And now here is a tasty example, but before we delve deep into this, I does anyone have any questions? Okay, that's good to hear. I guess, I hope. So this question is taken from SMMC of last year. This was the third problem in the first 3-hour section of the paper, I believe in both Asia Pacific and Europe. It's actually quite a nice question. We won't be doing the complete question, mainly the diagonalization part. But I'll let everyone absorb the question first and maybe provide some nice little facts. So do recall, this is a 2x2 matrix. That fact is gonna come in very handy. Also recall the fact that it requires m to the 2025, so we will need to do some exponentiation. Here, diagonalization would be one of the better methods. Alright, so I guess the most simplest way, like, there's some nice, neat other trick methods too, but say this is your first time seeing this. The most simplest way, assuming you remember Math 1B knowledge, would be to start off with diagonalization. So our first mission would be to find the eigenvalues. Now we can do it that way, or we can simply invoke the power of the trace and the determinant and solve it that way. So if you go back to the matrix just quickly, you see right there the trace is t plus 1 plus 1. So that means this guy is t plus 2. And if you go back using our AD minus BC formula, that is t plus 1 times 1 minus 1 times t. So it literally is, yeah, t plus 1 times 1 minus 1 times t. So it literally equals to 1, the determinant. And that gives our characteristic polynomial for finding the eigenvalues to be lambda squared minus t plus 2 lambda plus 1 equals to 0. I hope that part was pretty straightforward, just calling up some useful facts. So once we have found the eigenvalues, now this part needs, I guess, a little bit more intuition, but the key idea here is to recall the fact that the determinant is the product of eigenvalues. If we notice that the determinant of two eigenvalues, the determinant which includes two eigenvalues equals to 1, let's call them arbitrary lambda 1, lambda 2. We know that lambda 1 times lambda 2 equals to 1. And this means our other eigenvalue, lambda 2, could be a could be a reciprocal of lambda 1. This is a very powerful fact that actually what influences our substitution. Once we know that, we can essentially consider using, by making sure that t equals to lambda plus lambda minus 1 minus 2, what we are really doing is trying to factorize it in its essentially product of roots form. That is the rationale behind this substitution. Now I've just labeled it mu plus mu, 1 on mu, just for more visual clarity. So that is the rationale behind this substitution. And after that, we can express our eigenvalues in the form mu and 1 over mu, which I guess reduces the number of variables we need to be concerned about. And now our next job is to find eigenvectors. Now this is done in the same format as before, where we solve these two systems, the m minus lambda iv equals to 0 system. And once we solve it, we get these two expressions, and from that we can determine our vector. So just for more clarity, for visual clarity, the rationale is, if you just say for the, the equation 1 system, t plus 1 minus mu t and 0. When you examine these entries, you get t plus 1 minus mu v1 plus t v2 equals to 0. This means you can express your v1 in the form minus t on t plus 1 minus mu v2. And essentially then, once you choose a nice value for v2, you can get your v1, v2 eigenvector in a nice format. And here, some of the decisions we have made is essentially scaling them up such that they look nicer to display. Yes, yeah, they look nicer to display, yes. And eventually we will have accumulated enough facts to get P and the diagonal matrix, which means we can finally diagonalize it. But do remember, we need to find P inverse. So thanks to our handy inverse of a 2 by 2 matrix formula I had introduced before, we can just simply compute it like this. And through that way, we actually have an easier way to compute m to the 2025. Now, the rest of this solving is not that related to matrix diagonalization, but it does involve computing matrices, which is why it's being discussed. So once we have diagonalized in the form PDP minus 1, essentially this is the brute force part. There's a reason why some of these problems expect people to take like 45 minutes if they're doing a brute force solution, is that we will literally multiply these. And then from the first row, first column entry, we will get that. And from the second row, second column entry, we will get that entry. I know, right? Very funny expressions. But they're actually not that scary. Since we're looking for the roots of AT and BT, as defined by the original question, we will solve for AT equals to 0 and BT equals to 0. Now, once we ignore the so-called, I guess, impossible values, we will realize it's actually just either lambda n equals 1 or mu to the 2n equals to 1. They should be, sorry, that should have been a mu. Yes, that was a typo, yeah. Mu n equals 1 or mu to the 2n equals 1. Now, over here, I hope people remember a neat little thing from high school mathematics. Roots of unity. These practically express roots of unity in another form. And when we actually solve with roots of unity, we will get these values for our eigenvalues. And I mean, after that, we can continue substituting, get a value for t, and so on. But we will not discuss this in too much detail since our main purpose was diagonalization. But feel free to do this question in your spare time. It's actually quite a delicious question, very appetizing. And our worksheet will be even more appetizing. And yes, our next topic.
Hi, I will be talking about XOR basis. So, I mean, I think if you've listened to the rest of this workshop, you'll probably understand the basics of linear algebra. But some, 1141 fundamentals, or I guess 1241. A set of vectors is linearly independent.
Sorry. Because I wrote it whatever. It's like 2 slides, but whatever. Okay, so we're doing bases, so a bit of, once again, 141 revision. Yeah. First things first, linear independence. So we just call a sequence of vectors linearly independent if and only if the only combination that gives it 0 is if every coefficient is also equal to 0. So you can think of this either in this way or probably the easier way, which is if you have a set of vectors and you can represent any vector as a linear combination of some of the other vectors, then that set is not linearly independent, or it's linearly dependent. They're basically the same, same thing if you think about it. Like, you just have to move like one of the vectors to the other to get 0 for them to be the same statement. But I guess the interesting bit is that they are unique. So if it's a set of linearly independent vectors and we have some vector that's a linear combination of those linearly independent vectors, then the coefficients of the scalars that give the combination are unique if and only if it's a linearly independent set. This is also not too hard to prove from the definition of linearly independent. Like, I guess the easy way for one of the directions is if they're not linearly independent, then you can get some two sets of coefficients that give you the same vector, and obviously that's not unique. And yeah. And then the other side of linearly independent is span, like other side of basis, you have linear independence and you have the span. So the S, let S be like a finite set of vectors and a vector space, then the span of S is just all of the linear combinations of S. So that's, I guess, somewhat self-explanatory. And for bases is just like the combination of the two, right? You have some vector space, and a set of vectors is a basis of that vector space if it's number one, linearly independent, and number two, it spans the whole space. So I guess some things from there is if you have some n-dimensional vector space, you can show that it has n. The basis must always be there must always be n bases, because you have to have at least at most n linear independent and at most n linearly independent vectors and at least n vectors for it to be spanning. I think that's low-key all I have.
Sure. So with these 1, 2, 4 concepts in mind, we can now go on to our programming challenge. So our challenge is we are given some starting set of distinct integers, and we want to construct a closed set under the operation of XOR. So a set is closed under the operation of XOR if for any two numbers or vectors in our set, we can XOR them and the product will still be in our set. And the question is, if we have a starting basis or a starting set, what's the minimum number of new integers or vectors we need to add to S to make it closed? So this problem operates over a specific vector space, which is the vector space of binary numbers with some number of bits. We can call that D, for example. And all your normal vector space operations still apply. Addition, vector addition, is just defined using XOR. Is anyone here not familiar with the XOR operation? Two ones make a 0, two zeros make a 0, 1 1 makes a 1. And scalar multiplication is just there are only two scalars in this field, 1 or 0. So 0 times a vector is 0, and 1 times a vector is itself. Yeah, sure. Adding and reducing mod 2, or counting the number of bits and seeing if it's even or odd. So we want to count the minimum number of integers we need to add to S to make this closed. And you can think about this if I have a starting set, and by the laws of linear algebra, if I keep adding things into it, all I need to find is the minimum number of elements I need to add to form a basis. Once I form a basis, I know how big the span is. I can just subtract off the starting elements. So we can insert the integers of x one by one. If x is already in the span of the elements we have, the span does not change, right? Because x is a linear combination of the vectors we already have, so the span will not change. We can still express the same vector space with it. Otherwise, the basis grows by 1, and the span doubles in size. So the span doubles in size because you basically introduced a new bit. So everything you can represent again. This is obviously a specific property of our vector space, which is Z2. Now the question is, how quickly can we test this property, whether the new vector we add is in the span of our current vectors? So in linear algebra, this is testing whether some set is linearly independent. We could, of course, just check all 2 to the I linear combinations. The reason we can do this is because the only scalars in our field are 0 to 1. So you can just imagine our formula a1, x1, a2, x2. You can just try setting a1 to 0, 1, a2 to 0, 1. But 2 to the I is pretty slow, and if n is 25 in this problem, it won't pass. So to help us, we should consider the most significant bit in every binary number. So the most significant bit is basically the bit that represents the greatest value. So if everyone knows binary here, it's the first bit represents 1, 2, 4, 8. The most significant bit is the leftmost bit. So for example, the most significant bit of 4 is 2 because it's like, 1, 0, 0. 7 is 1, 1, 1. And if we have a basis where all the most significant bits are different, that means we can obviously order it such that the most significant bits are decreasing. And now it's actually much easier to test whether a new vector is in the span of this basis. And to make it a bit visual, let's say I give you some current set, 26, 15, 3, and 1. You'll notice that the most significant bits of these binary numbers are in descending order. And I can ask you, is 20 in the span of these numbers? Now, it's not like so easy that you can just like look at it, but like if you think about it for a bit, you can sort of just like clearly, yeah, like 20 has to be XORed with 26, 15, that has to be XORed, and then 1 has to be XORed. So you can conclude that 20 is the XOR of 26, 15, and 1. Because it is in the span of our current set, we should not add it to the set. So the point of the algorithm in the previous slide is that if we have some number that we want to test, we can repeatedly XOR it with the members of our set in descending most significant bit order, right? If the XOR is less than the current number, we replace it with the XOR. Now, this min property is not it's not very intuitive, but I guess the idea is, going to the previous slide, if you XOR 20 with 26, what happens is that the most significant bit, which is like the 4th bit, turns to 0, right? That bit is the only deciding factor for whether it will be less. So if it's less, as in if we choose the min, clearly the most significant bit got wiped, got replaced. So in general, this computes the minimum value of A XOR V. So the new vector that we add and every XOR of every vector in our current span. So the reason it's correct is that we really want to show two things, right? The first thing we want to show is that if a certain vector gets added into our set, it's definitely independent. We can't form it in our span. The second thing we have to show is that if it's independent, it definitely gets added to our set. We don't want to avoid adding vectors into our basis. The second direction is actually easier to prove. If it's independent, there's absolutely no way that it could get reduced to 0, because that means that if it gets reduced to 0, it must be a linear combination of some elements in our set. So that direction is easier to prove. To prove that if it's added, it must be independent, you have to consider the most significant bit. And you can use the property that for any XOR of the elements that are already in our set, the top bit is at some most significant bit that's already in our set. So if we have an A that doesn't get reduced to 0, it definitely must not be in our span. So, we can walk through an example here with 9. We're going to XOR 9 with not 26, with 15, and then I think with 3. But eventually we are not going to reach a final value of 0. So we will add 4 to the set, not 9. 4 because that will preserve our most significant bit property. And in the next slide, you can see we can add 4 such that all the most significant bits still remain distinct and in descending order. Now, implementing this in C++, we do have the option to keep the most significant bits descending. You can do this. You can use a vector or a set and then insert it in that order. You don't actually need to. So you can just keep the vectors that or the numbers that are currently in your basis in any order and apply this min operation. I don't actually know the proof for why this works, but it does work. So the code for it ends up being very, very nice. It's just like, basically like a few lines. So for every x, we add it to the basis, we keep minning it, and if it gets reduced to 0, that means that it's in the span, we don't add it, and if it's not reduced to 0, we can add it to the basis and expand our span by 2. Does anyone have any questions about this algorithm? Good. Oh, sorry, yep. Yep. Sure. So adding, let's say we add a new integer or a new vector that's not in our current span. That vector is going to add one extra degree of freedom to our span, right? And since we're operating over the vector space Z2, or only 0 to 1s, because if you imagine every binary number is just made up of 0s and 1s, right? So if you add another bit to our span, it's going to double, because you can produce everything you had before and everything you had before with that one bit in the new location. Yeah. Yes. Yes, if you have 5 in your basis, your span is size 32. If you increase that basis size to 6, it will be 64.
So we're going to skip this topic and we'll just go to the last topic, which is linear transformations. That should only take about 10 minutes, and so we'll wrap it up there. For those of you that are interested, this would just be going over basically the question of what happens when you can't diagonalize a matrix. How do you find a nice closed exact form for a matrix power or a matrix exponential or something involving working algebraically with matrices and trying to decompose matrices. We're going to skip that, and this last section on linear transformation shouldn't take too long. So I'll present the first part of this. Just credit to Daniel, who's not here today. He wrote the slides for this part. I'm presenting for him. So let's get started, and after that, you can all have your pizza and everything. So linear transformations are a specific type of function that we care about when we are dealing with types of vector spaces. So, specifically, the way I like to think about it is a linear transformation is a function that preserves the operations and structure that we care about in vector spaces. So the key property, if you combine those two that's written up on the board, is that when you take the transformation of a vector u plus a scale multiple of v, it preserves this addition property, and it also preserves a scalar multiplication property. So v. And so the worksheets are over there. And so why is this useful? To put it a bit vaguely, and we'll see one specific example related to competitive programming. This is useful because we can then say that if it's easier to think about certain problems and certain vector spaces in terms of another vector space, we can preserve and map that property to another vector space and work in that one. And the outcome of this slide, as well as talking about when we are doing this linear transformation, which links to how this whole part of this whole workshop, we'll be talking about matrix exponentials, matrix powers, matrix diagonalization. The way that we are meant to think of linear transformations is through a matrix. So you can represent every single linear transformation with respect to particular bases, bases we spoke about in the previous section, as a matrix, and vice versa. So there's actually a correspondence between linear transformations and matrices that's also itself a linear transformation, if you care to say. But now the actual problem that we will be working through, this is one of two problems. This is a more math-focused problem, and then Yoshi will take us through another problem. For this one, we are leaning into a bit of an adjacent topic on linear transformations in terms of distances between particular points, in terms of norms. For this problem, best to see by a little picture briefly. So the setup is we have a series of n points in R2. Well, we could actually, yeah, we're dealing with R2, let's say. You could generalize this problem to higher dimensions. We are starting off with the Chebyshev distance. Manhattan distance. So the Manhattan distance comes from the Manhattan metric. You may have also heard of it as the taxi cab metric. So if we deal with points x1, y1, and x2, y2 over here, the distance between the two, this notion of distance we will be defining is going to be the sum of the horizontal and the vertical distances between the points. So we would take x2 minus x1 and y2 minus y1. So we would add them together. Our goal in this problem is to find the maximum distance between any two pairs of points. So if we were to look at our diagram, we would think to be looking for something visually where we are looking for 2 points that are diagonally as far away from each other as possible. The difficulty, though, is how do we account for the fact that we have to walk both right and upwards? And so what we can do is, the reason why this is under the, instead of being able to solve it exactly, we are going to do a transformation of coordinates, in fact a linear transformation. Let's talk about a similar problem. So usually when you, in higher study, if you would learn about the Manhattan distance, accompanying it usually is as well a similar type of metric of comparing how far apart 2 points are. The Chebyshev distance, distance, if we look back at our diagram, instead of taking the sum of the two horizontal and vertical distances, the Chebyshev distance takes the greater of the two. So in this case, the Chebyshev distance would just be, if the x-coordinate, the horizontal of your triangle, is the larger one, then that's the one that you care about. And so let's just pretend for a second that that's the problem we were dealing with. If we were to try and find the maximum Chebyshev distance between any pairs of points, we could write it in this manner, where we are taking the maximum over the maximum of the delta x and the delta y. Again, in your triangle, you have the horizontal and vertical distance, in which case, does anyone want to tell me how we can do this efficiently? How can we find the maximum Chebyshev distance? Just yeah. So if we were to say look at the diagram, what we could look at is, if we look at this first component, the delta, the distance between xi and xj, that would be, to try and get that as large as possible, we take the maximum value of xi and the minimum value of xi. So in this case, I'd look for the 6 here and the -7. And likewise, I would do so the same for the vertical coordinates. And so what the answer would be, if you were, I guess, wanting to write it out, would be the maximum of, let's say, maximum of max, so write xi minus min xi, and you can do the same for the y coordinate. So max minus min. The kind of intuition here is you only really need to look in those two directions. You only need to look to your right and to look upwards. That is what becomes important. Whereas before, when we were dealing with the Manhattan distance, it became more complicated because we were trying to look both right and down sometimes. And so now we're going to take this original problem that we had of dealing with the Chebyshev distance, and we're going to transform it into a problem of dealing with the Manhattan distance. The way that we do that is somewhat algebraic. Let's just walk through the details. The way you can visualize it is, if you look at, this is kind of the reasoning for why this works. There's a lot of algebra there. But if you look at a point, let's say the origin, there's this notion of what's called a bull in when you deal with norms. What you can visualize is, if you look a specific distance away, so if we look a distance of r away, then with respect to what we just looked at, which was the Chebyshev norm, like this, every point on this square would be 1 unit away from that center point 0, 0, whereas what we were originally looking at, which was our Manhattan distance, again, we were looking at this distance r, but now, if I dot this, now the distances of the points at which are exactly r distance away would form this diamond. And so specifically, the transformation that we will end up doing is this 45-degree rotation. which will be the same in the second problem. We'll do this 45-degree rotation to get from our original problem, which was dealing with the Manhattan distance, to our Chebyshev distance. With this here, we have an algebraic way so we have here in terms of our Manhattan distance, we have this algebraic way to rewrite the sum of the delta x and delta y, the difference in x coordinate, difference in y coordinate, in terms of the maximum of two values, which smells at least a bit more similar to our Chebyshev distance. And so that's motivating what this transformation would be, where it ends up being our substitution of A and B ends up being this 45-degree rotation. And so we can change this into looking at the maximum of of this A plus B and A minus B. Okay, so we have a little diagram there, but the outcome that we want to see, as we had before, we had that this was our answer when we were just dealing with the Chebyshev distance, and the game that we are playing here is to go from our Manhattan distance and our x and y and transform that into I guess vectors with respect to a different coordinate system where we are rotating 45 degrees and then solving the problem in that new coordinate system. Okay, so I won't go too much further on this. I'll just leave Yoshi now to quickly go through this last problem. But I'll be happy to field questions after, when we're having pizza.
Thank you. Okay, so we're looking at this problem where you have a grid, and on there each cell is colored either red or black, and you want to find the largest red diamond. So a diamond is kind of like defined as this shape, and like the size of the diamond is determined by its length across. So like 1, 2, 3, 4, 5 rather than like 1, 2, 3. And what this question, like the solution to this would be, is that instead of looking for the largest diamond, we want to look for a largest square. And I guess from before, we can see that if you take some points, like in Manhattan distance, if you make the transformation, it's going to turn into like the square. So this diamond, once you do the transformation, is going to turn into this red square. And so looking for the largest diamond is going to be kind of hard because it's kind of weirdly shaped, and you might want to expand from the middle or something, which might take a while. Instead, we can like turn all diamonds into squares and look for the largest square that way. Yep. Were people like turning the slides with this? Okay. So let's say we were to try to find the diamonds. What might we do? Like, for example, we might say, well, the diamond has to have a center somewhere. So let's try every center point and spread out until like we hit something that's no longer red, like in our diamond, and then we stop. And then if we want to try every center point, that's like n squared points. And then if we want to like make large diamonds, that's going to take n squared time to check for each center, which is like n to the 4, or like it's a bit better than that, but that's not great because like our constraints were 500. N to the 4 is a bit too slow. So yeah, let's try to turn this into squares. Okay, so the transformation is the same as the one before, which is the one that takes xy to, is that like, yep. So the transformation again, I'll just like write it down. You turn xy into x plus y, x minus y. And what this does is that it flips it across the x-axis, it rotates it 45 degrees, and it spreads it out. So that diamond again will turn into that square. So that's a diagram of it. And essentially, like that top guy is going to flip across and go to this bottom guy there. Like that one is gonna like go to the top, and then so all the corners become the corners in this new square. And the other thing that we need to be careful of is that not all of the cells in the square are going to get filled up. because like the transformation does stretch it by a factor of root 2, which means that the area of the square is going to be larger than this. And what's the other thing? Oh yeah, and it's also true that the length of the square is going to be the length of this diamond, because kind of like you can think of each side gets stretched by a factor of root 2 and then it spins around, and so it just kind of covers that square. Okay, cool. And here's like, I guess, about the holes. So like again, this is the transformation. So if like x and the parity of x and like so like x and y and x minus y are either like both odd or both even. So some squares, like for example the black ones on this chess grid, are never going to get mapped to, so they won't be colored. We can ignore them. So we kind of only focus on like the white squares, or the ones that can get mapped onto. And for something to be a diamond, we need a square area to be like the white squares, and a square area to always be like red. So the ones in blue should all be red, whereas the ones like white, that's white right here, like doesn't really matter because they never get mapped onto. Okay, so I guess now that we have a way of turning the diamonds into squares, we can just kind of like look for a square where all of the ones that are relevant are colored in. So all of these blue ones have to be colored in. We can do this with a prefix sum. And I guess that's the number of squares in a diamond given its side length. So if the side length is k, then there are k squared plus 1 over 2 cells in that diamond. And yeah, and a way that we can count this quickly for each possible diamond is that we can have this prefix sum here, and this cell tells us how many blue squares there are from between here and like here. And so this cell is going to tell us, this cell is going to tell us how many blue squares there are in total in the grid. This like for example is going to tell us how many blue squares that there are in this subsquare. And you can do that by DP. I probably won't go into how to do it specifically, but yeah. So once you have that, we can, so if we're interested in if like this subsquare, for example, is a diamond, then we can look at this cell minus this cell. And that's going to tell us how many blue cells, like blue colored in cells, there are in this area. And if that is equal to like k, which is 3 squared plus 1 over 2, which it should be in this case, then like that tells us it's a diamond. And yeah, the other thing is that we don't know how big the diamond we are looking for is. So I guess we can try all the different sizes a diamond could be. But another thing that we can do, yeah, that's okay, sure. The other thing that we can do is we can binary search, because if we have like a diamond that's of size, say 10, then we always have a diamond of say like 9, because like within that diamond is going to be another diamond. Yeah. And then, so I guess what's the time complexity in this case now? So the new grid is going to have dimensions, like that depends on the previous grid, and it gets scaled by a factor of root 2, and it gets rotated kind of, so we also need to give it some padding. So the root 2 in each direction gives us like, it's times 2 the area, but we also need to pad the edges, because after you spin the square, it becomes a diamond, so we need to kind of like pad the diamond to make a bigger square. So in total, it's going to be like 4n squared size, which is still O of n squared. And then once you do the prefix sum, which like to do the prefix sum, it's O of 1 per cell in the grid, which is O of n squared, because there are n squared cells in total. And then we need to search for the squares, and that's gonna be, so like to look to see if there are any diamonds of say size like 7, you need to check like all possible locations where the 7 big diamond can be, and that takes O of n. You can try that for like several values of n, but yeah, we can do that with a binary search. So you try some value of k to see if there's a diamond of size k. If there isn't, you try some smaller value. If there is, you try a larger value, and so that reduces it like from a factor of n to log n. So overall, that's going to be n squared log n, which is faster than like n to the 4, or a bit better than that. And I guess the main optimization for this question is that instead of looking at diamonds, we turned it into squares, which is like cardinal. So instead of having like things going in strange directions, everything within that grid is like within what you're looking for is all like in the square, which allows you to do prefix sum. And then once you have computed the prefix sum, it can be queried in O1. Any questions, I guess?
All right, can we get a round of applause for the presenters for today? Okay, so I'm sure everyone can smell the pizza. Before we have that, we need to just get a photo with the banner. So can please everyone come to the front. If you haven't scanned the QR code for attendance, please scan it here. If you have any feedback, please also scan the left QR code. You have your worksheets now. Please feel free to ask us if you have any questions as you're working through those. These slides will be uploaded, so there's a few items in the appendix if you want to have a look through them or if you want to review them. The recording for the workshop is also going to be uploaded. Okay, sure. We will take a photo. Can someone help me hold the banner? Feel free to have the pizza now. We'll open the boxes. Thank you everyone so much for coming. We'll have more events coming up. Tomorrow there's the Rookie Code Crumble, Cookie Code Crumble workshop. Sorry, competition. And there's also a competition on Thursday, which is the Wit collab. Yes. And there is also a crochet workshop on Thursday with free bubble tea if you go that direction.
I mean, I just quote